Okay, so now that we've talked about equilibrium and Le Chatelier's principle and the stresses and shifts, now it's time to get a little bit more quantitative. So what topic covers that? It's referred to as the equilibrium constant or the equilibrium constant expression. And we'll use the Haber process to differentiate between what's meant by the equilibrium constant expression, what's meant by Q, and what's meant by Kc. Okay, so as a recap, this is the Haber process reaction. Ammonia plus hydrogen makes, nitrogen plus hydrogen makes ammonia. Everything's in the gas phase. And so if you can determine the relative concentrations of reactants and products, they can get put together into sort of an equation, a mathematical equation. And you always put product concentrations on top and reactant concentrations on the bottom. And that is equal to Kc. So this whole thing that I've drawn here is what's sort of a generic version of the equilibrium constant expression. Sometimes it also gets referred to as the equilibrium law. If you want to look at one that's specific for a given reaction, for this reaction right here, the Kc equals ammonia on top in brackets, and ammonia is squared because in the equation, ammonia has a 2 as a coefficient. So whatever the coefficient is, that becomes the exponent on that concentration. And as a recap, if we haven't done it before, these brackets equal concentration. So it means a value in moles per dm cubed is being plugged into this expression. Okay, on the bottom is nitrogen. Nitrogen has a coefficient of 1, and therefore it's just raised to the first power. And hydrogen has a coefficient of 3, and therefore hydrogen is raised to the third power. Nitrogen and hydrogen concentrations here are being multiplied, not added. So this is the equilibrium constant expression for the Haber process, for the reaction listed above. Now, to actually determine the Kc value, we would need to plug in concentrations, numeric quantitative concentrations, at equilibrium. So equilibrium constant expression, and then the value of Kc is determined by plugging in actual concentration numbers into these spots in the equation when the thing is at equilibrium. Well, the units of Kc are going to come down to, the fact that the brackets represent concentration. So every bracket represents mole per dm cubed, mole dm minus 3. So if on the top I have that squared, and on the bottom, if we combine terms, I essentially have that to the fourth because I have N2 to the first, H2 to the third, and when I multiply things, the exponents add. And so let me fix, nope, there we go. Okay, so we got it to squared on top, and I've got it to the fourth on the bottom. And so if you know your math, essentially that's going to cancel out the squared on the top and leave you with 2 or squared on the bottom. It's going to remain on the bottom. So it's going to be 1 over mole per dm cubed as the overall units. If you want to rewrite that, it could be mole per dm cubed to the minus 2. And if you want to rewrite it further, you could actually put that minus 2 onto both of these units, and you'd end up with it's mole to the minus 2, mole to the minus 2, and now it's dm to the positive 6. Because when you carry out this exponent here, it multiplies to the exponents on what's inside the parentheses. So it requires that you know a fair bit of math in terms of how to deal with your exponents, but it's nothing too wild and crazy. All these superscripts. So you could be asked to come up with an equilibrium constant expression, or once you've done that, you could be asked to look at it and then determine the units on that equilibrium constant itself. And all that means is you recognize that every bracket represents mole per dm cubed. So you have to carry out that exponent on every concentration. In this case, the squared cancels and the 4 cancels down to a 2. That's why we end up with 1 over concentration squared. That's the same thing as concentration to the minus 2 because it's on the bottom of the fraction. And then if we multiply minus 2 times 1, and we multiply minus 2 times minus 3, that's where we get minus 2 and 6. Okay, how big Kc is, the magnitude of Kc, can give you some really useful information about a given reaction at equilibrium. So a large equilibrium value, right, essentially means that at equilibrium you have a lot of products relative to the amount of reactants. Okay, so in equilibrium language, we say that having a large Kc value implies that products are favored at equilibrium and that the products are more stable, right? So that you'd probably end up with more products. But really, we can just point out that the products are favored at equilibrium, or the position of equilibrium lies to the right. That's another way to say that same thing. You're going to have more concentration of products at equilibrium. That gives you a large Kc value. Well, a small essentially means the opposite, which is that reactants are favored at equilibrium. The position of equilibrium lies to the left. So some equilibria reactions, very few products end up getting formed, and most of it stays as reactants. And in that case, you'd end up with a very small Kc value because the bottom of the fraction would be larger concentrations than the top. So you can have very small Kc values as well. And if the amount or the concentrations of reactant products are almost the same at equilibrium, then the Kc value ends up being pretty close to 1. Really, it could be somewhere between this value and 0.01 and like 100 would still imply relative amounts of both reactants and products are about the same, because if they're about the same when you plug them into this expression, the top and the bottoms will be pretty close together in value. So Kc will be pretty close to 1. So those are some things you should be able to recognize about the magnitude of Kc. Okay. Some other things to discuss when you're talking about Kc. The concentrations of products and reactants are plugged into it and give a quantitative measure of how they compare, and that's known as the position of equilibrium. Okay? For a given equilibrium, the Kc will not change unless the temperature is changed. So it's locked in stone for a given temperature. All the other stresses that we add to a given system at equilibrium cause shifts. So they may cause you to make more reactants or make more products, but that is only to maintain the value of Kc. So Kc does not change as a result of those stresses and shifts. Temperature, however, is different, and it does affect Kc. So you kind of have to lock it in that temperature is the only one that causes that effect. So if we are plugging in concentrations and we're at equilibrium, then we are calculating Kc. If the system has not yet reached equilibrium, so we just mix stuff and it's still reacting, and the two rates don't equal each other yet, if we plug concentrations, non-equilibrium calculations into the Kc expression, we will get out a different value. We will get out the reaction quotient, Q. Okay? So it's the same exact equation, it's the same Kc expression, but because we're not at equilibrium, when you plug in the concentrations, you won't get out the Kc value. You'll get out some different number. So they refer to that as the reactant quotient Q. The value of Q can tell you in which direction the reaction is still proceeding, or in which direction it will proceed in order to get to equilibrium. So if Q is smaller than Kc, so if you're told a Kc value and then you're also told a Q value, and Q is smaller, that means the forward reaction is still favored at this point. So the forward reaction is happening more than the reverse reaction. If you think about what Kc is, you've got, again, products on top, reactants on the bottom. So if Kc equals 10 and Q is only 8, well, that means the top of the fraction isn't big enough yet. So it means that we still need to shift to the right. So again, to try to clarify, if Kc is 10, just to make up a number, and Q is 8, that means in terms of having products and reactants, you still need to make more products, because in the expression we put the products on the top and the reactants on the bottom. And so by shifting right, you'll make more product, and that will make the value of Q go up until it equals Kc, which is 10, until it reaches equilibrium. Okay, so a value of Q that's lower than Kc implies a shift to the right. I'm not sure why I drew all these arrows and things up here. That was supposed to go down below. That's might be tricky to pull off. Let's see what we can do. Do that. Almost. Check it. Oh, okay. We might have salvaged it. Okay, we're gonna just leave it like that. Now I gotta do this. Q equals 8. Okay, if Q is larger than Kc, then that implies the reverse. Well, sort of for obvious reasons. If Q is bigger than Kc, that implies that you've got too much product relative to the amount of reactant. And so some of the product needs to turn into reactant in order to bring the value back to the Kc value. So if Q was 12 and Kc again is 10, then some product needs to turn into reactant to bring the value back down to 10. And if Q equals Kc, that implies that you are at equilibrium, right? If you plug concentrations into the Kc expression and you actually get the Kc value, that means you are at equilibrium. So the only difference between Q and Kc is it's the same equation. So for the Haber process, this is the same expression. If you plug in concentrations at equilibrium, you get Kc, the value of Kc. If you plug in some other concentrations when it's not at equilibrium, then you get Q. Okay, we'll do some practice questions like this in class. So I'm going to skip over this page for the time being. Only temperature affects the value of Kc. So all the other stresses don't change it. I'm also going to skip this for the sake of the video. You can read through it, and I show you mathematically why that is the case. So now we can talk about the effective temperature. Okay, I'm going to skip that for now, though. So when the temperature changes, it does affect Kc. So again, let's consider that this Haber process is exothermic, meaning it's delta H negative. Okay. So we should know as a general rule from the other class that an increase in temp always favors, so increase in temp always goes in the endothermic direction. So if our stress is increasing temperature, our shift will always be endo. Yeah, our shift will always be endo. Well, for this reaction, because it's called an exothermic reaction, that means the forward reaction is exothermic and the reverse reaction is endothermic. So an increase in temperature will shift this reaction to the left, and your reasoning is because that is the endothermic direction. It favors the endothermic process more than it favors the exothermic process. So even though it makes both actually forward and reverse rates faster, it makes the reverse reaction even faster. And so if you think about Kc, if you cause a shift left, that means you're making more of the reactants and you're making less product. So more on the bottom and less on the top will mean that the Kc goes down. So if you see that a Kc decreases, that means that whatever happened to temperature must have made a shift to the left. So a decrease in Kc means a temp change caused a shift left. And again, remember, it has to be a temp change because unless it was a temperature change, a shift left would not have caused the Kc value to go down. This only happens with changes in temperature. Okay? A decrease in temperature for this particular reaction would cause a shift to the right because a decrease in temperature will always favor the exothermic process. It will slow down both rates, but it will slow the exothermic rate down less. So in this one, it would make more of the product. So products are on top, that would increase. Reactants are getting used up, so the reactant concentrations are decreasing, and both of those will have the effect that the Kc will go up. And so a An increase in Kc means that a temp change caused a shift to the right. And so if we had an endothermic reaction instead, the increase in temp would shift it right and therefore make Kc go up, and a decrease in temperature would shift it left and cause Kc to go down. Okay? And I'm going to skip these examples for us to talk about in class. The last page, the last thing to talk about in the video is just that sometimes equilibrium or reactions get written with different coefficients, right? So if this is the normal reaction, sometimes we know that, if we're talking about Hess's law or something, we sometimes double coefficients in order for the moles to work out, or we flip reactions or invert them so that the products are written as reactants, reactants are written as products. So just to show you mathematically what's going to happen, it's basically one idea, which we've already talked about, which is the coefficients in the reaction have to do with the exponents in the Kc. So if this is the original expression up here, and we've got all the coefficients are just A, B, C, and D, then this is the equilibrium constant expression right here. If I invert the expression, or the reaction, so now I took the products from before, and now they are the reactants. I took the reactants and I made them the products. Well, now it flips the Kc. So the new Kc would be in the inverse of the original one. It would be 1 over Kc. Or in other words, it's Kc to the minus 1. Remember that when I flip a reaction, it's essentially like multiplying it by minus 1. So I've essentially I've multiplied all the coefficients by minus 1. That caused them to flip sides. And so whatever I do to the coefficients, I do that as an exponent to the Kc value. If I doubled all the coefficients, that would put a little 2 next to each one of these guys, each one of the coefficients. And so I could pull that out if it was the same, and I could pull out those extra little 2's here as a squared. So it's going to be whatever the original Kc value was squared. Again, whatever I do to the coefficients, so this is 2 times all the coefficients, that's what's going to happen to Kc, but as an exponent. So the Kc value is going to end up being squared. So that's just how the math works out. So same idea, if I triple the coefficients, I would end up with Kc cubed. Whatever I do to the coefficients, I do that as an exponent to the Kc. And if I half them, well, halving something is, so you could say it's raised to the half power, which is fine, but raising something to the half power is actually the same as taking the square root of it. So one way to write it would be that. The other way to write it would be this. Okay, so those are, I can't imagine more than 1 or 2 marks here, but it's just sometimes we flip around equations or we change their coefficients, and the Kc will respond in this one way. Whatever you do to the coefficients, that's what will happen to the Kc, but as an exponent. If you add together 2 reactions, then you have to multiply their Kc values together, because right, if you add things, then exponents end up. The relationship is that the exponents sort of multiply. So, anyways, that's the final thing to remember about equilibrium constants. The most important things are being able to set them up quickly for any reaction. That's going to be always going to be on the exam. Solving for units, and most importantly, really, is knowing how they will change with changes in temperature. So this page here, the effective temperature on Kc, and it depends on if it's endo or exothermic. The changes in temperature can cause changes in the Kc value. We'll do some practice in class. That is the topic.